Hey everyone, so today we're going to be working on problem number 4 from the AP Calculus BC 2021 free response questions from the exam. Question 4 reads as such. Let f be a continuous function defined on the closed interval -4 less than or equal to x less than or equal to 6. The graph of f consisting of 4 line segments is shown above. Let g be the function defined by g of x equal to the integral from 0 to x f of t dt. Part A asks, on what open intervals is the graph of g concave up? Give a reason for your answer. So first, it's very important to state that g prime of x is equal to f of x. By stating that the graph f of x is the derivative graph of g of x, therefore to find the upward concavity, we look for the intervals on g prime of x equal to f of x that are increasing, which on the graph as you see right here is from negative 4 less than x to less than 2, and 2 less than x less than 6. And that right there is our interval, the open intervals on where the graph of g is concave up. And it is also worth mentioning that because the question asks for open intervals, we do not have any equal signs in our interval answer. Part B asks, let p be the function defined by p of x equal to g of x times f of x. Find p prime of 3. So as you can see, what I've written here is just the equation p of x equal to g of x times f of x. When we take the derivative of p of x, we get g prime of x times f of x plus g of x times f prime of x. When we plug x equals 3 into the equation, we get p prime of 3 is equal to g prime of 3 times f of 3 plus g of 3 times f prime of 3. As you can see through my various equations in orange here, we sought out to find g prime of 3, f of 3, g of 3, and f prime of 3. Let's start with g prime of 3 first. To find g prime of 3, g prime of 3 just equals -3 because we know that g prime of x is equal to f of x, and right here is the graph of f of x. So saying g prime of 3 is also the same as saying f of 3. And if we go to find where f of 3 is located, f of 3 is located right here, and f of 3 is equal to -3. So that would be our value here for g prime of 3. Meanwhile, f of 3 is also equal to -3 because, as we said before, g prime of 3 is equal to f of 3, so they both equal -3. Now to find g of 3, we actually have to plug the x equals 3 into the equation g of x is equal to the integral from 0 to x f of t dt. And so we're going to get g of 3 is equal to the integral 0 to 3 f of t dt, which is going to be equal to 1/2 times 1 times 4 minus 1/2 times 1 times 4 minus 1/2 times 4 plus 3 plus 1. Because we're essentially finding the area under these parts of the graph here, from 0 to 1, and then from 1 to 2, and then from 2 to 3. So 1/2 times 1 times 4 minus 1/2 times 1 times 4 cancels out because it just equals 0. So then we're left with -1 times 7, which is equal to -3.5, which is our value for g of 3. And then f prime of 3, as we see here, is pretty much the slope of this line right here, since x equals 3 on the graph of f lies on this line. And so we do rise over run. So if we move up 1, 2, 3, 4 units up, and then 1, 2, 3, 4 units to the right, that's our rise over run. So that would be the slope of the line. So we have 4 over 4, which is equal to 1. So once we plug in all those values into the equation here, p prime of 3, we get p prime of 3 is equal to -3 times -3 plus -3 times 1, which is going to equal 9 minus 3.5, which then is going to equal 5.5. So the value of p prime of 3 is equal to 5.5. Part C then asks, find the limit as x approaches 2 of g of x over x squared minus 2x. So first, in order to solve this problem, let's just plug in x of 2 into g of x over x squared minus 2x and see what happens. So the limit of x approaches 2 of g of x, because it's our numerator, equals g of 2, which is equal to the integral 0 to 2 of f of t dt, which is equal to 0. We had proved previously in part B how the area under the graph from 0 to 1 and the area above the graph bounded by the x-axis from 1 to 2 is equal to 0. Then by just plugging in 2 into the denominator x squared minus 2x, we also get 0. So 0 over 0 is indeterminate. So because our equation is indeterminate, because our answer is indeterminate, therefore we need to use L'Hopital's rule. In L'Hopital's rule, we take the derivative of the numerator and the derivative of the denominator. And so we'll be left with limit as x approaches 2 of f of x over 2x minus 2, because remember, as we said above, g prime of x is equal to f of x. So the derivative of g of x is g prime of x, which is equal to f of x. So that's why we put f of x in the numerator here. And then the derivative of the denominator, x squared minus 2x, is equal to 2x minus 2. So the limit as x approaches 2 of f of x over 2x minus 2 is going to be equal to f of 2 over 4 minus 2, which is equal to f of 2 over 2. And f of 2 is equal to negative 4 because on the graph, as we can see here, f of 2, the value of f of 2 is negative 4. We plug that into our equation here, so we get negative 4 over 2, and then our final answer is negative 2, which is what the limit as x approaches 2 of g of x over x squared minus 2x equals. And finally, part D asks, find the average rate of change of g on the interval negative 4, 2. Does the mean value theorem guarantee a value c, negative 4 less than c less than 2, for which g prime of c is equal to this average rate of change? Justify your answer. Now, our general equation for the average rate of change is f of b minus f of a over b minus a. So therefore, for part D, we're going to apply our interval negative 4 less than or equal to x less than or equal to 2, this interval here, into our formula here. So then we're going to get g, we're going to treat b value as 2 and treat our a value as negative 4. So we're going to get g of 2 minus g of negative 4 over 2 minus negative 4, which in turn is going to equal the integral of 0 to 2 of f of t dt minus the integral of 0 to negative 4 f of t dt over 6. Now we will rewrite our equation as the integral of 0 to 2 f of t dt plus the integral of negative 4 0 to f of t dt to keep things going from the smaller value on the bottom part of the integral to the larger value on the top of the integral. Then we can combine both integrals to be negative 4 to the integral of negative 4 to 2 of f of t dt over 6. Now comes the big math. Finding the area above and below the graph bounded by the x-axis, we are going to get 1/2 times 6 times 2 plus 1/2 times 6 plus 4 times 2 plus 1/2 of 4 times 1 minus 1/2 of 4 times 1 over 6. Now we know that 1/2 of 4 times 1 minus 1/2 of 4 times 1 is just going to cancel out because it equals 0. So then we're going to be left with 6 plus 10 over 6 because 1/2 times 2 cancels out, so then we're just left with 6, and then the 1/2 times 2 here cancels, so we're just left with 6 plus 4, which is equal to 10 over 6. Then 6 plus 10 over 6 is equal to 16 over 6, which then equals 8 over 3. So therefore, 8 over 3 is the average rate of change of g on the interval negative 4 to 2. However, we still have the second part of part D to answer, which is, does the mean value theorem guarantee a value c, negative 4 less than c less than 2, for which g prime of c is equal to this average rate of change? Justify your answer. So here I have my whole explanation. Because f of x is equal to g prime of x is continuous on negative 4 less than or equal to x less than 2, equal to 2, g of x is differentiable on that interval, and thus it is also continuous on that interval. G of x is ultimately differentiable on negative 4 less than x less than 2, and therefore the mean value theorem guarantees a value c on the interval negative 4 less than x less than 2, such that g prime of c is equal to g of 2 minus g of negative 4 over 6. And that right there is the answer to part D. Thank you.